They're good to go.
All right. Yeah, thanks, Tracy. Thanks to Holden for hosting us as always. So today we're going to go through a few different compliance updates for high percentage outdoor air equipment specifically. Looking at the agenda, a lot of it is going to be focused around the A2L refrigerant transition. Obviously, that's a hot topic right now as we get into 2024 for some of the deadlines coming up in 2025. So Eric will cover that, looking more at the background of this refrigerant transition, how it came to be, some important information there. Looking at the codes that have to be updated in relation with this A2L refrigerant transition, and then getting into some design practices. Some of those will change. They may be different from what you're used to when you're designing jobs. So going to cover some of that. And then I'll jump back in and cover some DOAS efficiency updates, specifically IEER versus ISMRE 2, with some things coming down the pipeline there as well. So my name is Jake Bamke. I'm the product manager with our dedicated outdoor air systems business unit here at Greenheck. I started at Greenheck in 2018, spent the past 5 years really on the application side. So supporting Holden, supporting you guys on more of a pre-sale front, focused on codes, compliance, applications, how it relates to the systems that you're designing. So moved in the product manager role in August, just in time for this fun refrigerant transition. But good thing we have Eric here to help us. So I'll pass it over to Eric to introduce himself, and then he will take you through the A2L stuff.
All right, thanks, Jake. I'm Eric Gerben. I'm the Principal Regulatory Compliance Engineer here at Greenheck. My role is primarily focused on our heating and cooling products. I have another counterpart who's dealing with air movement and control products. So he's dealing with fan regulations and stuff like that. But really, I started at Greenheck in 2006. I've started out in the makeup air engineering team, so learned a little bit about furnaces, direct gas, indirect gas fired furnaces in the past. Got into the energy recovery side of Greenheck business. Worked my way up through there, helped design some of our initial DOAS product offering back in the late 2009, 2010 era. And then did a stint as controls engineering manager up until about last April. And that's when I started in this role. We knew there were a lot of regulatory and compliance issues coming up for Greenheck Group, whether it was new product efficiencies, which Jake will cover later on, or the refrigerant transition, which we'll talk about today. But yeah, I've been here since 2006. I'm starting to feel a little old now that Jake's on board, and he's only been here a couple of years. So we'll get started on the A2Ls here. All right, Jake. Oop, we're moving in the right direction. Okay, so when we talk about refrigerants, generally we were speaking about HFC phase down. So we talk about refrigerant transition. This all started with HFC phase downs, and it started by the United Nations with a global agreement quite a few years ago. What we're talking about reducing hydrofluorocarbon chemical emissions into the atmosphere. And it's going to be done globally through this United Nations agreement. It's going to be done on different schedules based on a country's developed status. So there's Article A5 and non-Article A5 countries. That's the United Nations terminology I don't quite understand. But basically, if you're a developed country, you're going to work on your HFC phase downs a little bit faster than you are if you're a non-developed country. And the reason we're doing it is because HFCs trap radiant heat in the atmosphere. That's kind of like the high-level overview. When we look at HFCs in the atmosphere, most of the HFC emissions come from air conditioning or refrigeration in one way, shape, or form. So most of the regulations we're talking about target our industry. There are other industries that are impacted as well. So like motor vehicle air conditioning units, I think most of us are aware, our air conditioners in our vehicles switched over to refrigerant 1234YF a few years ago. We also use refrigerants in industries, like even for our foam panel process, we used to use hydro or HFCs to spray our foam panels. And since we've moved away from HFC refrigerants altogether for foam panels. And it's used in aerosols, solvents, and other end-use products as well. So when we talk about HFC phase down, it's more than just the HVAC industry, but we are definitely the #1 user of HFC refrigerants. On the right-hand side, I put kind of a graphic up here to describe what the refrigerant heat trapping capability of HFC refrigerants are. And the EPA's rulemaking documents that kind of reference that there's been studies that have measured the amount of HFC refrigerants in the atmosphere. And based on the 2020 measurements that have been made, we're trapping about 0.037 watts per meter squared of radiant heat in the atmosphere. So if you look at the goals for some of these transitions, you'll see reducing that down to 0.015 watts per meter squared is really the goal of the HFC phase out, or phase down, I should say. This is a phase down, not a phase out. So really, this whole HFC phase down actually started back in 1987. It set up the framework when we were worried about ozone depletion, and we went through some transitions with CFCs and HCFC refrigerants. That was all based on the Montreal Protocol, which was the United Nations agreement back in 1987. Back in 2016, however, as we've been monitoring HFCs and their impact on the environment, the United Nations got together again and came up with the Kigali Amendment. And that kind of set the goals for all the countries to meet their HFC phase down requirements. So that was just a general agreement. And then from that Kigali Amendment on the United States side, we had to turn that into a regulatory framework. So back in 2020, end of 2020, there was an act signed by Congress that was called the AIM Act. And that gave the EPA permissions to start regulating HFCs. And since then, the EPA has been continually releasing different rules that affect different parts of the industry. And I'll go through that here in a second. So a lot of the rulemaking has just come over the last 2 years on how the refrigerant transition is going to work. I think we've all kind of heard, whether we've been at ASHRAE shows in the past or heard from other manufacturers. I mean, we've been expecting this since 2016 and even prior to that. But now the rubber's hitting the road, so to speak. These are the phase down targets for the US in general and the Kigali Amendment. And you'll see the dates on the US side lag the Kigali Amendment target dates, but we got started a little bit late with the regulatory framework. In general, we're trying to hit these targets. So the first steps aren't so bad. We're kind of in this 40% reduction target now, and that's really where we're seeing a lot of the refrigerant transition happen. As we get further along and we get towards the 2034, 2035 time frame, there's some bigger jumps we have to make as well. So I'm not really sure what's going to happen at that point. There's a lot of things that go into the regulatory framework, which I'll cover here in a little bit. But I'm crossing my fingers and hope we don't have another refrigerant transition in the next 6 to 7 years. So the EPA rules that are referenced up above in the timeline, there are 3 different types of rules the EPA has regarding HFC phase downs. The first is an allowance rule, and that sets the amount of refrigerant we can import as a country and produce. So I put the 2023 and 2024 allowances there. So you see we've reduced quite a bit the amount of HFC production we have, and that's a weighted average. So it's pounds of refrigerant times the global warming potential. So it's not, you can't really look at that as pounds of refrigerant, but it's really the global warming potential of the refrigerant as a whole, and it's a weighted calculation. So 2023 looked a lot like 2022. There weren't any refrigerant restrictions really between those 2 years. 2024, we take a little bit of a hit here on what we can produce in terms of refrigerant and what we can use. So that's the allowance rule. The SNAP rule, it really evaluates potential new refrigerants for applications. So there was a SNAP Rule 23, which was released a couple years ago, that identified new refrigerants that we can use in our industry. It started with just R32. The more recent ruling put in the 452s and the 454 refrigerants. And those can be used for air conditioning and heat pump applications. There are many other acceptable refrigerants out there for different applications, but I'm going to really focus our presentation on air conditioning and heat pump systems and really our high percentage outside air systems. So that tells us what refrigerants we can start to use. And at the end of the day, they'll actually go back and delist some refrigerants like R410A and tell us we can't use those any longer, but that'll be a couple years down the road, more than likely. But really where things started to take effect is when they came out with what's called the technology transition rule. What that does is it says for air conditioning and light heat pump applications, we can no longer use a refrigerant that has a GWP above 700. And that will start in January 1st, 2025 for the country as a whole. If you've been out to the West Coast or been following California, they've set their own refrigerant transition rulemaking, very similar timelines, very similar limits to the US. We have to follow both as a manufacturer. So we're watching whatever states have done their own GWP limits as well as the Department of Energy. But the EPAs. The EPAs does affect the whole country, however. So this is really where things hit the road. When we talk about the technology transition, these are probably the big questions most people have. We as a manufacturer have to stop producing new R410A products on January 1st of, oops, I put the wrong date there, 2025. So my apologies there. I've been working on safety standards. We had to switch by that date. So next year, January 1st, 2025, we can no longer produce new R410A products, but manufacturers can produce R410A components. So like a good example of that is I can produce, we at Greenheck Group don't, but other manufacturers produce residential outdoor condensing units. As long as it's a component, which that would be a component, not a complete product, they can continue to manufacture that for replacement only. So we'll still see R410A outdoor units getting manufactured, but they can only be used in replacement of existing equipment. And there's some rules on replacements, what constitutes a replacement in the field. So it gets a little bit goofy because we're talking about products versus components. Mainly what we sell at Greenheck is the products. Then you also have a sell-through period. So we stop manufacturing on January 1st, 2025. You can install new products up to 3 years after the manufacture date. So we can install products up until the year 2028. If you're developing a system, so like a split system, you only have 1 year to do that. I'm not really sure why the EPA chose to give 3 years for products and 1 year for systems, but that's what they chose to release in the rulemaking. In fact, HRI had to fight to get that year back on systems because it was down to 0 years. So when we're talking about a system, that means something you have to specify the components for and put the final charge in the field. So as long as it's packaged and it's charged at the factory and you put it in the field, you get that 3 year sell-through period. The other thing for us is reporting requirements. We have to report how much HFC refrigerant we sell. We'll have to start doing that with our 2025 sales. And then EPA will start tracking that in general. So after the EPA went through all of these rulemakings, I'm kind of curious what refrigerants are left for air conditioning systems and heat pumps. So here's the list of what's left is allowable that meets the 700 GWP limit. And the EPA has decided you can use it for air conditioners and heat pumps. And you'll notice a lot of those are A2L refrigerants, a couple A3s, and then ammonia is still listed, mainly as ammonia absorption systems. And you can see the GWPs there, but there's conditions of use limits. So we can't retrofit any old system. So we couldn't take like an R410A unit, change out the compressor or change out components, and then run it with 454B. There's too many safety issues to pull that off. So that's really where the EPA has allowed replacement components indefinitely for our 410A systems. So we can keep those running as long as we can. The bigger issue though is the safety of the new refrigerants. So we're going through the process of listing the new safety standards, and that's what the EPA requires when you switch to these new refrigerants. There's also OSHA requirements and particular service training requirements for the service industry on how to address these refrigerants. But with what's left, we're left with A2Ls, which are lightly flammable, and A3s, which are highly flammable. And hopefully you've seen the ASHRAE 15 chart on the right that describes the classification of refrigerants. So A's being your non-toxic refrigerants, B's being your toxic, and then the number 1 being the lowest flammability, no flammability, up to 3, which is a very highly flammable gas. So we're doing great things for the environment, but guess what? We brought in a safety risk for the occupants of our space or occupants of our designs. So that's really where things get a little crazy here. And as I've been digging a little bit in my role, what's interesting is, ASHRAE 15, the mechanical codes have addressed flammable and toxic refrigerants in the past, but mainly for mechanical room installations. So we as an industry have understood that for a while, but what's new is we're requiring this in direct high probability system. And a direct high probability system is an air conditioner or heat pump. And it's where a refrigerant leak in the refrigerant circuit can directly enter the occupied space. This is really what's new. and really where the safety concerns come from. To use these refrigerants safely in the industry, we've had to touch almost every code and regulation imaginable. On the regulation side, OSHA's been impacted all the way to the Department of Transportation. So how we ship products to you guys, there's new requirements and loopholes we need to jump through. On the building code side, everything from the fire to the energy efficiency codes get impacted in some way. And I use energy efficiency loosely, mainly because nothing's really changed there, but we're redesigning products on our end, so we have to make sure we meet the existing energy efficiency requirements with this refrigerant transition. So a challenge for us as manufacturers. When we talk about standards, we've got refrigerant classification like ASHRAE 34, all the way to product safety like UL safety standards that you'll see on most products. The hard part, though, is with all this new change coming in the industry, there's lots of owners. So different groups own different portions of standards and codes and regulation development. So there's a lot of opportunity for confusion, and there's lots of effort. I mean, some of these codes, man, I've never seen updated in my time in the industry. So it took a lot more effort than I think one wants to admit. So there's a lot of chance that we have editorial oversight, and there's a lot of times where assumed knowledge isn't actually documented in a code or standard. So as I've been reading through, I might find little nuances that just don't make sense, and been reaching out to our industry experts that we're connected with to try to understand these a little bit better. When we talk about safety, the industry has been doing quite a bit. Organizations like AHRI, ASHRAE, and the EPA have invested a lot of money in testing equipment at UL, at other third-party labs to make sure we've properly identified and mitigated any risk with these new lightly flammable refrigerants. And they've had to go through and create new product safety standards. So on the air conditioning and heat pump side, if you're familiar with specifying UL 1995 or just coming across that in the past, we have to transition all our products over to a new standard, which is an internationally harmonized standard with US and Canada specifics, and that'll be UL 60335. And then each product will have its own type 2 standard, so every product goes through a type 1, so there's a 60335-1 that applies to all products. Heat pumps will go through a -2-40. Refrigeration equipment will go through a -2-89 version of the standard. And most codes will start seeing this, like the International Mechanical Code will be updated to show these new standards in place of 1995. The other part from the safety standpoint is mitigation strategies. So there is a risk of flammability. There is a risk of a light explosion. The probability is very low and requires a very high ignition energy source, whether that's a spark or an actual open flame. Those are probably the only two things that will light the refrigerant. Those are things we have to watch out for. But we can address those by looking at the charge size of our equipment, making sure if it does leak into the space, it won't reach flammable levels. We can look at air movement strategies or air replacement strategies to get the refrigerant well mixed and out of the air, so we mitigate that risk completely. The safety at a high level is always based off of your largest circuit charge serving a space. So if you're doing DOAS with VRF, obviously you got refrigerant in the DOAS system, you've got refrigerant in the VRF system. What we're looking at from a code compliance standpoint is we're looking at the largest circuit, where it can leak, and then using that to determine our mitigation strategies. So we don't have to combine the refrigerant in the DOAS with the refrigerant in the VRF and add those together to come up with a mitigation strategy. We're just going to look at those two systems independently. And really at that point, we're assuming one major leak incident per system. The types of mitigation strategies that are out there to help us avoid any issues with safety starts with refrigerant charge in room area. If your room area is large enough and your refrigerant charge is small enough, you may not have to do anything. It'll leak in the space. It won't accumulate to a flammable level. And you just buy the unit, you probably don't even need refrigerant leak detectors for that type of a system. But as we look to shrink the rooms, or let's say you have a unit that's ducted and you're ducting air to the general space and then to somebody's office, we have to start thinking about, would that refrigerant leak to just that office space? And what should we do in case that happens? Because usually the office spaces are relatively small. We have to consider that the refrigerant could go there. So then we start looking at air circulation strategies. If you're doing like an air conditioner that just serves one room, we could use air circulation in that equipment just to keep the air spinning in that room and avoid any accumulation of refrigerant. When we're talking about ducted systems, we're going to try to keep zone dampers open and run the whole system at minimum airflows to make sure the refrigerant can mix well between all the spaces that ducted unit serves. And then if we're doing really high charge equipment, we might have to get into a ventilation strategy where we bring in dedicated mechanical or natural ventilation to get refrigerant out of the space with a ventilation strategy. So these are the kind of options that we have available. The UL safety standard helps us decide which ones we're allowed to use. There's a certain charge per refrigerant that you can't go above and have it be an air conditioner or a heat pump, depending on the refrigerant flammability level. I think, quoting this off the top of my head, I think for R454B, it's 189 pounds is really where the limit, charge circuit limit comes from for that refrigerant. Probably the heartache for the year of 2024 will be getting state codes updated. AHRI has been trying to do a good job of monitoring state-by-state adoption of building, fire, and mechanical codes. It's hard to keep track of, and everybody does it a little bit differently. We'll talk about Georgia here in a little bit on how they adopted or updated their code. But every state's done it different. There's 3 codes to monitor. You can't do it on a simple US map like I have on the left there. And you notice Georgia's red. It's actually green now. We've had some updates in Georgia, so that's a good thing. But a lot to do. So actually, AHRI, around the time of the HR Expo, is hoping to come up with an interactive map so we can see state by state which codes have been updated. Are there any issues with the safety standards, or are there any issues with maybe a technical glitch on how something was amended? They'll have all that on an interactive map, so we'll be looking for that shortly. Georgia's in a pretty good spot from what I can find, so just a couple nuances we'll talk about here in a little bit. Just from a code perspective, the mechanical code is really going to be important to be updated for us to actually use an air conditioner in a building, starting in 2025. The building and fire codes, however, deal a lot more with warehousing of equipment. So, if I've got a warehouse and I'm going to store, a bunch of outdoor air conditioners, a bunch of DOAS products, there's going to be a limit to how much refrigerant I can have in that space until the building and fire codes get updated, because they're going to treat it like propane. They're going to treat it like natural gas until those codes are updated. And we found in our own manufacturing facilities, we've been struggling with that because state codes haven't been updated fast enough for us to leverage the low flame propagation properties of these refrigerants and store more refrigerant in our buildings and be a little bit more efficient on our manufacturing side. Georgia code status, I was looking at this last night. There were some amendments done to the 2018 version of the International Mechanical Code to come up with the Georgia Mechanical Code. I was looking through it last night. I didn't find a whole lot that concerned me. The one thing that did concern me, though, is Georgia's missing R454B in their refrigerant table. So that'll be something we'll try to get updated this year through AHRI to make sure we can use that refrigerant. One challenge, too, is they treat A2Ls as a subclass of A2 refrigerants. From what I can read, that was never the intent of ASHRAE Standard 15. They're supposed to be treated as independent refrigerant classes. So there could be some confusion when you're looking at the code. Do the requirements for A2s also apply to A2Ls? And it's a little convoluted the way the code was updated to understand that. So there are some nuances there. AHRI is actually going through the process of creating state-specific amendments to get pushed into each state for 2024 to get folks all the way to having a nice clean code set to start using A2L refrigerant for air conditioners and heat pumps. One other challenge we have is there's a lot of hands on the cookie jar, so to speak. So when we talk about charge limit requirements and mitigation strategies, there's multiple standards, and I put the pecking order here. So and numerical values. So when it comes to charge limits, the IMC or the UMC, if you design on the West Coast, those obviously like to take priority. They're going to reference a product safety standard, which is UL 60335. Those have charge limits in them as well. Turns out those safety standards reference ASHRAE 15. for guidance as well. And then ASHRAE 34 recently added some LFL limits as well. So we've got three different levels of code authority in regards to charge limits, and then they're not all written the same. So we're trying to filter through that and figure out, okay, what's the real charge limit requirement that we should be operating at? So right now we're working with AHRI and ASHRAE to kind of help clear some of that stuff up. The other ones there are as exciting. The charge limits are probably the most exciting is leak detection. But again, a lot of hands in the cookie jar. We're trying to figure out where's the industry going, where have we made editorial mistakes that need clarification, so we need a cleaner answer out to everyone. From a design practice change, these are the things that kind of stand out to me. One is we have to understand space limitation requirements. When we go and list our products to UL 60335 with flammable refrigerants, we're going to have to give you a minimum floor area requirement, depending on the mitigation strategy we've chosen for our equipment. So I may say, you know, I've got a 5-ton unit. I need to have 10,000 square foot of area to install that. Those are things we'll have to be aware of, and the design teams will have to be aware of those safety standard limitations. And again, the International Mechanical Code and Uniform Mechanical Code have their own dispersal volume calculations. And they're based on pounds of refrigerant per 1,000 foot cubed. Or if you are looking at future codes, it's MCF is the new 1,000 foot cube terminology. We're going to have to consider that. We're going to have to do those calculations. In general, we're doing analysis here on one of our buildings to see if we replace 30-ton units, what would that look like? We could replace the 30-ton units. The only issue we had was those units are ducted to individual offices. So we're going to have to use a mitigation strategy where we allow the central multi-zone unit, so to speak, continue to run its fan indefinitely in case we detect a leak. So little things there that we need to be mindful of. You'll have to do communicating and non-communicating spaces. So building design might get changed depending on what you're dealing with. I think with the mitigation strategies we have in the industry, if we keep the supply fan running in the case of a leak, where there's probably not too much that will change. If we're nervous about doing that in any designs, there are wall barriers and open ventilation requirements that we probably want to meet to avoid having to run the supply fan. I don't think that's going to be an issue, but just something I'm looking at as we choose what mitigation strategy we go forward with at Greenheck. And then the room design, like I mentioned, you might need to have grills and registers at the bottom of the floor that are open so the refrigerant can leak into adjoining spaces. That's only if you're getting really, really complicated using high charge equipment. Hopefully you guys don't have to deal with that, but something that our team needs to be educated on. Big picture for the industry, kind of where we're looking, we need to follow the 2024 model code requirements. There's a lot of mistakes, or maybe not mistakes, oversights in the previous versions. We need to get everybody up to what the 2024 model codes are today. Those have all been published, but not adopted. We need to leverage our product listings, so the UL 60335 listings for our products, to understand what the minimum floor area requirements are. And then we're also going to have to understand how that plays into building size and volume calculations. And from a safety standpoint, there's really three aspects to making sure that this refrigerant can be used safely. One, we want to avoid collection of refrigerants approaching flammability levels. Two, we want to keep the air moving in the event of a leak if it is a larger charge system. And then the third is we want to avoid high energy ignition sources. And that's mainly done on the product design aspect. So there'll be stuff in the mechanical code where you don't want to expose refrigerants to open flames above 700 degrees C, I think is what it is. Those are things in a mechanical room we'll have to be concerned with, but in general occupancy, we don't have to worry about those things. And then be prepared to do your minimum floor area and dispersal volume calculations to make sure that you have enough space in the event of a leak that it becomes, you don't have an issue and you can address it with your mitigation strategy. And it looks like I left an and there. Oh shoot, that's an update on your side, Jake. And then just general building design. There might be things you choose to do a little bit differently with mechanical ventilation if you're doing like a mechanical room, or if you're trying to make sure that like a confined office space does let refrigerant bleed out into other adjoining spaces. What steps remain for us at Greenheck? Right now, we're in the midst of A2L compliance testing. We're actually doing some testing down in Plano, Texas at Intertex Lab. We have another engineer over in Minnesota taking a look at some of our products over there. We do have to go retest and recertify our equipment. We've already moved our products to the 60335 standard, but it turns out the way they're planning to release the safety of it, they're going to reevaluate A2Ls as a new product type. So there's more testing and more certification we have to do on our end. We'll be doing simulated leak testing with A2Ls to make sure our refrigerant leak detectors pick up the refrigerant before it becomes an issue. We're going to look at ignition sources and make sure we eliminate or control all ignition sources in our equipment well. And then for us, we design a lot of the HVAC industry's 20s. So like if you're familiar with the Pareto principles, the 80-20s, we do a lot of unique stuff in the market because a lot of the volume's on light commercial and residential side. So sometimes the answers aren't there for our products. So it would be my job and the engineering team's job to go close those knowledge gaps in the industry and make sure we have a clean answer for everyone. We're going to continue to evaluate our mitigation strategy choices. I think where we're headed right now is we'll probably put refrigerant leak detection on all of our equipment, but there could be some smaller stuff where we're not required to need it. And then for us, the biggest one, we've all dealt with supply chain risk issues back in after COVID started. It has put a tremendous pressure on the industry. We're figuring out when we can get all our components in from our vendors to make a clean transition to the new refrigerants. So that's what's left for us. I think Jake, I did leave resources in here. So if you're curious, there are some industry resources out there. If you go to AHRI's website, they have a safe refrigerant transition portal. You can see the studies they've done, the testing they've done, recommendations they have for storing refrigerant cylinders. All that's out there. It's a great resource. If you like punishment and reading regulations, you can go to EPA's website and look at that. Definitely get familiar with ASHRAE standards 15 and 34. And then the International Code Council, which does the International Mechanical Code, Fire Code, and Building Code. They have some resources out there that describe what changes are required to get to the 2024 model codes. And it's a good oversight. So if you want to see what's changing in an easy to do format, they have PDF documents out there based on the code version you're currently on. All right. Jake,
Fantastic.
hand it over to you.
Yeah, thanks, Eric. Now everybody on the call knows why we have an in-house regulatory expert. There's definitely a lot changing right now. So with that said, I know today we wanted to share a little bit about our transition plan, but just due to everything that Eric shared, still a lot of things that have to be decided yet, questions that have to be answered. So we are planning on having an upcoming webinar, so keep your eyes out for a message from Holden, hopefully around the April timeframe, where we can really provide an update on some of the things that Eric talked about, the codes, the design practices, see what else has changed in between now and April, get into our transition plan. Obviously, we're getting towards that January 1st, 2025 date where we'll have to have everything manufactured with 410A. So what that transition plan looks like, working through those details, and then any outstanding questions, obviously any questions that you guys have as you use the resources, but also things that we find answers to with questions we currently have. So that is the bow on the A2L stuff. One other thing before we get to your questions, it looks like, judging by the icons, we have quite a few questions, which is great. But I wanted to cover DOAS and rooftop unit energy efficiency requirements. And so I'll start with IEER. When we look at IEER, something that likely most people on the call are familiar with, but that is your integrated energy efficiency ratio. And what that looks at is a weighted efficiency measurement for package and split system units, looking at your overall capacity and comparing that to the power input it takes to get to that capacity. And so the way IEER is calculated is you have 4 different conditions, all carrying different weights. So this is the ambient air for each one of these tests. For instance, point A is your full capacity condition. That's only 2% of your calculation. So it's 98% weighted towards those part load conditions, which is extremely important when you look at what components we utilize for the high percent outside air equipment to be as efficient as possible. The one thing with IER though, is that your entering evaporator coil temperature is always the same regardless of your 4 points. So you could be changing your ambient conditions, but we're saying that entering air into the coil is always going to be 80-degree dry bulb, 67-degree wet bulb. Represents that mixed air condition. And when you look at the test standard for this is AHRI 340-360. This test standard was really designed for units that are about 25% outside air and less. And when we look at how we explain DOAS or high percent outside air units, we're really talking about that 25% outside air and above being that true kind of DX DOAS in our mind. And so that's really where you're seeing a transition to ISMRE. And there's ISMRE has been around. It was in the newer versions of 90.1, some of the newer IECC code updates, and this stands for Integrated Seasonal Moisture Removal Efficiency. And when you look at that definition, it's very similar as far as looking at different weighted conditions as an efficiency measurement, but this time it's looking specifically at your pounds of moisture removed compared to your power instead of just your overall capacity. And when we look at how this is tested, this is really representing a 100% outside air unit. So we still have 4 different conditions. You'll see that the weights do change a little bit from the IEER, so a little bit more weighted towards that full load condition, but still significantly weighted towards how efficient you are at part load conditions. And those conditions entering the coil actually match what is outside. So that's why we're saying this 100% outside air unit, this true DX DOAS, and that is test standard AHRI 920. And so anytime that you're looking at codes or you thought about newer versions of 90.1 or IECC, there was that clear separation of if I am a DX DOAS unit, 100% outside air, with or without energy recovery, I have to follow my minimum ISMRE values, not IEER. I say with or without energy recovery because we're looking at how efficient we are at removing moisture. And for our total enthalpy energy recovery devices, we're removing moisture without as much power required at that time. In this picture, you can see there's an energy wheel. So we would be removing moisture before it even entered the coil, but we're still looking at our outdoor conditions being that entering unit temperature. So when you look at ISMRE minimums, there will be different requirements or different minimums for units with energy recovery and units without energy recovery. So where this really is important is we started this update last year. So the Department of Energy, really in July of this last year, started requiring manufacturers to list a value. And we had to list an ISMRE 2 value. We'll talk about the differences there on the next slide. But May 1st of this year, so coming up in a few months here, now we're actually going to have to meet minimum requirements. So when this rolled out in July of last year, from a manufacturer standpoint, it was really to get familiar with the test strategy, the compliance side of things, but there wasn't actually a minimum that was implemented by the DOE at that time. Currently, there will be moving forward as of May 1st. Prior to this ISMRE 2 value, the Department of Energy only federally regulated IER for manufacturers. Obviously, your certain codes like 90.1 and IECC, things like that, they had ISMRE, but from a federal level, that was not something that was regulated. So now we will get that true separation between the partial research style units and then moving into that true 100% outside air DX DOAS unit. I mentioned ISMRE 2 is really what the Department of Energy is going to regulate. So the question is, what changed between the first version of ISMRE and the second, and why did it change? Well, reheat is no longer required, and that's because different applications may or may not require it. So it's not always required by code. Sometimes it's not even allowed per code. So they wanted to take that out of the testing process with this ISMRE 2. Also, you can no longer over dehumidify and take credit for it. So in the past, there may have been situations where the system was using more energy, but it was overshooting your low dew point set point. So manufacturers were taking credit for that over dehumidification to get a better rating. But now they're a little bit more strict as far as what you can actually take credit for when you're removing moisture. And then the last 3 are really just changing some of the static pressures, changing some of the weights, and then changing some of the conditions. And that is really to make sure that before they started to require a minimum ISMRE2 value, they made sure that this test standard was up to date and more realistic based on the industry standards. And so from a cooling efficiency comparison standpoint, really this pulls everything back into one table. So the difference between ISMRE and ISMRE2, you can see it's still AHRI 920, just updated to that 2020 version. And then the big things to point out are really the evaporator entering air conditions. We talked about how when you're at that 25% outside air and less, you have a lot of consistent recirculation. And that's really draw those conclusions on those applications. That is geared towards more of that traditional rooftop unit, maybe a VAV system without energy recovery. Get into the ISMRE or ISMRE2 applications. Now we're really that true DX DOAS with that separation of do we have energy recovery or do we not have energy recovery? I know currently we're really working with some of the codes to determine what happens between that 25% outside air and 100% outside air. So this is certainly not a perfect code compliant standard at the moment because there are situations where we have high percentage outside air, let's just say 75 to 80%, when all of a sudden it may not work. So we will go forward with questions now. That is everything that we had from a compliance standpoint.